How's it going? Welcome to the final presentation for the Solar Optimized Land Autonomous Recharge and Intelligence System, SOLARIS. We are Team 12 and we attend the University of Central Florida. Behind the project, we have 4 engineers. Ryan Markowitz, a computer engineer who's our software lead. Raphael Puig, an electrical engineer who's our power lead and PCB design co-lead. Nathan Hammond, an electrical engineer who's a PCB lead and the power co-lead. And Garrett Fortier, a computer engineer and hardware software integration lead.
Now time for a quick background on why we made Solaris. A normal solar panel is passive. If it ends up in shade, it just loses power and stays there. Also, most setups don't tell you anything about how much energy you're actually pulling into the system. What we wanted to do was make the panel move and make it talk to you. To do this, we added telemetry information going to a phone app via Bluetooth Low Energy between Solaris and the user's phone. Also, Solaris will automatically detect if it is in shade and move for optimal power gains over time.
Some of the goals for our project require us to operate in 3 different modes via a Bluetooth app. We want to operate in a stationary mode where the solar panel moves back and forth, an autonomous mode where the robot notices a lower light level and tries to move to higher light level, and then a manual mode where we can control the robot via joystick over Bluetooth. Other than that, the solar panel just has to rotate in 2 different axes to move towards peak sunlight. To cover some of our engineering specifications, we hope to be able to move the robot at a max forward speed of greater than 0.3 meters per second, and this is controlled by the motor drivers designed by us. We also hope to be able to angle the solar panel tilt and rotation to a limited number of degrees to avoid damaging the robot itself via encoders. And we also hope to achieve a Bluetooth Low Energy range of 1 to 6 meters based off the Bluetooth Low Energy specifications.
This is the hardware block diagram for Solaris. We've divided the project into external, internal, and remote systems. The external system features outdoor-facing equipment, most importantly being the solar panel. The internal system contains the energy monitor and inertial measurement unit sensor, as well as controlling devices. Lastly, the remote system contains the phone app, which allows direct wireless communication between the user and Solaris.
Now we will go into the technology and part selection of our 5 subsystems, each with their own deep dive. And we will go in order of control, drivetrain, solar tracking, power, and then last, communications.
When making a pick for our control unit, we looked at a few different candidates of microcontrollers as a MPU like a Raspberry Pi or an FPGA seemed a little overkill for our project. Lasering in our sights on kind of what made our project special, we fell to the ESP32S3. Some of the positives about the ESP32S3 that we focused on were its integrated Wi-Fi and Bluetooth Low Energy capability, its extensive GPIO density, and then of course the price to performance was hard to beat, as well as the support online for programming, which makes it an easy candidate for a senior design project.
We compared several brushed DC gear motors based on torque, speed, gear ratio, encoder availability, and cost. Although each motor met our speed requirement, the Go Builda 5204 Yellow Jacket delivered the highest torque and the greatest gear reduction while remaining competitively priced. This provided additional torque margin for the Solaris platform without increasing system complexity or significantly impacting the cost.
Now I will be going over the light sensor technology selection for Solaris. This is how we sense light, and it does 2 jobs: deciding which way to drive out of the shade and pointing the panel at the sun. We only need to know which side is brighter, not exact values, so we chose phototransistors for the job. They have built-in gain, so one resistor gives us a usable signal with no amplifier like a photodiode would need. A published study also showed that there was a measured 40% more signal than LDRs, and they're easier to implement than I2C parts since 4 identical I2C sensors can run into addressing problems. For us, it's just an analog read. After choosing phototransistors for the technology selection, there are about 4 phototransistors that made the most amount of sense for Solaris. For the actual part, we picked the TEP 5600. Its 20-degree viewing angle is narrow, which gives sharper contrast between the lit and shaded sides, and the contrast is the signal that we track on. It responds to the visible range, so sunlight doesn't get skewed by infrared, and it's through-hole, so we can mount it on the chassis of the robot.
We spent a lot of time deciding which battery chemistry would be best for our project. We landed on lithium iron phosphate for its high energy density and high safety factor. We selected the 20 amp hour Renogy battery for Solaris. This battery had the highest operating temperature range, as well as competitive pricing.
For voltage regulation, we compared linear and switching regulator architectures based on efficiency, thermal performance, complexity, and cost. Although linear regulators provided a simpler implementation, their efficiency decreases as the voltage drop increases, resulting in greater power dissipation. Because Solaris is a battery-powered platform, we selected a switching regulator to maximize efficiency, extend battery life, and reduce thermal stress despite adding design complexity. After selecting a switching regulator architecture, we compared several regulator ICs based on efficiency, output current, implementation complexity, and cost. Although newer regulators offered higher efficiencies, they also increased cost and design complexity significantly. The LM2679 provided the required 5 amp output current, a straightforward implementation with smaller passive components, and a proven reliability record, making it the best overall choice for both our 3.3 volt and 5 volt regulator designs.
For our energy monitor IC, we selected the INA228. This IC features robust electrical characteristics, as well as providing 8 different measurements accessible through I2C communication.
Now I'll be covering the ultrasonic sensor selection for Solaris. This sensor is for crash avoidance. We're running 4 of them, 2 facing forward and 2 facing back, mounted at the corners of the robot. We did the geometry on beam angle and sensor offset beforehand, and what fell out of that was a target beam angle in the 40 to 45 degree range with about a 10-degree offset on each sensor. That kept the blind spot in front of the robot manageable while still leaving good room to turn. Working from that, we picked the MB1020.
Selecting an inertial measurement unit for our project, we first initially stopped on the BNO 085. After some more researching and prototyping with it, we found that it had an extensive library, making it very difficult to work with. So we pivoted to a just as feature-rich ICM 20948. With this, we had 9 degrees of freedom, so we were able to use gyroscope data, magnetometer data, as well as accelerometer data. And it was very easy to communicate with over I2C. Plus, the price tag was much better than the BNO 085.
For the phone app for Solaris, our front end was written in React Native. This is a front-end mobile framework written in JavaScript. Our back-end decision was FastAPI, which is written in Python. The database that we chose was PostgreSQL, and it's hosted on Supabase. Our authentication provider is also provided by Clerk. Now I'll cover the wireless protocol selection for Solaris. This is how the phone and the robot actually talk. We compared Wi-Fi, Bluetooth Classic, BLE, LoRa, and Zigbee, and eventually we went with Bluetooth Low Energy. The biggest reason is that I can connect straight to the phone with nothing in between. LoRa and Zigbee have great range and great power numbers, but a phone can't connect to either of them directly. You would need a separate hub or gateway, and that's extra hardware and setup we didn't want for a simple one-to-one link. So realistically, it only came down to 2 choices, Wi-Fi and Bluetooth. BLE matches exactly what we're sending, which is low rate telemetry and short control commands, so we're not paying for bandwidth that we're not using. It draws less power than Wi-Fi or Bluetooth Classic, which matters on a solar system. It's also well supported in mobile development, so it kept the app simpler. The one trade-off is range. Bluetooth LO Energy doesn't have as much range as Wi-Fi, but since the robot is meant to be controlled by someone standing nearby, we are okay with accepting that trade-off.
To use a microcontroller, we have to be able to program it. And to do so, we use embedded stack platforms like Expressive, Arduino IDE, or Platform IO. In the case of our project, we made a split between ESP IDF, which is Espressive's solution for their microcontroller, and Platform IO, because both were functionally the same. Both have a native FreeRTOS integration, unrestricted peripheral access with library accessibility, and also both offer access to official toolchain usages, which meant that we could program with ease.
This slide highlights the completed motherboard, which integrates the ESP32S3 USB programming bridge, sensor interfaces, and external subsystem connections into a single PCB. During the layout process, component placement was optimized to minimize trace lengths, separate power and signal routing, and simplify connections to the motor drivers, regulators, and peripheral boards. After fabrication through JLC PCB and assembly, the board was successfully brought up and validated, providing reliable communication with the onboard peripherals and serving as the central controller for the Solaris platform. This slide highlights the completed H-bridge motor driver, from the original schematic to the assembled PCB. The design is centered around the V&H 5019 motor driver, which provides bidirectional control of the 12.8 volt brush DC motor. PWM and direction signals from the ESP32 are optically isolated to protect the control electronics from motor transients. To conserve GPIO on the ESP32, a logic inverter generates the complementary direction signal required by the H-bridge. During layout, high current traces were kept short and wide, with local decoupling and bulk capacitance added to improve power stability and suppress switching noise.
The Energy Monitor PCB is very critical to our project because it sits in series between the battery and the rest of the system and measures net power to the battery. Most notably, this circuit features a 20 milliohm 4-terminal Kelvin Sunsein resistor that maximizes the fidelity of the differential voltage read by the IC. Our light sensor is a simple circuit consisting of a phototransistor shunted to ground through a 10K ohm resistor. We manufactured shading devices that allow Solaris to achieve an understanding of where the sun is located relative to the robot. Our 3.3 and 5 volt switching regulators sit directly on the main PCB. We sized components on the regulators so they would be rated to source a maximum of 3 amps continuous current. Our mechanical realization of Solaris closely matches our CAD rendering. Because of the multi-purposeful T-slot rails that we built our chassis out of, it was very easy for us to mount ultrasonic sensors and light sensors at each corner of the robot. Additionally, the dual-axis solar mount system works perfectly to allow precise orientation of the solar panel towards the sun.
Here is the overall software flowchart for the firmware of Solaris. On power startup, we initialize all devices, and then we will wait for the phone app to connect to Solaris. Solaris starts in the manual mode, but the user, once they connect, can choose between 3 different types of modes. They can choose between manual, automatic, and stationary. In the background, there's other running tasks such as logging tasks and reads to the energy power buffer, which will later be used to make a move decision in the automatic mode if that is chosen by the user. This slide shows the control flow for the 3 operating modes. It's one state machine at its core. The firmware runs in a single loop, checks which mode it's in, and after each pass, it peeks the command queue to see if the phone has asked to switch. Since all 3 modes share the motors, and mutex controls who gets to move. On the left is the manual control. A throttle and steering command comes in from the phone app, and the firmware tries to grab the actuated mutex without waiting. If the panel is already moving, panel motion has priority, so the command just gets dropped. Otherwise, it blends the input into left and right motor speeds, caps them at 75%, drives the wheels, and releases the mutex. The middle one is stationary mode, which tracks the sun in place. It reads the light sensors, compares brightness side to side and top to bottom, and nudges the pan and tilt motors towards the brighter side until the panel is completely balanced. On the right is the automatic control, the most involved of all three. It ties tracking together with driving. It checks whether the panel is in shade, picks a direction from the sensor readings, rotates and drives the rover toward it, then checks the encoder for the expected power gain before deciding whether to settle or try moving again. These are three background subsystems, and the key thing is they all run in parallel as their own free RTOS tasks, completely independent of whichever control mode is currently active. On the left is power reading. Once a second, it samples the panel's power and state of charge, adds it to a rolling history, and keeps a second separate history while the rover is driving. Every reading also nudges the move decision task to let it know fresh data when it is ready. The middle one is a low power move decision. It waits for the nudge from the power reader, then roughly every 30 seconds it compares recent power against the recent baseline, which lets it ride out short dips like passing cloud cover. If power is actually staying low, it signals the controller to make an automatic move toward better light. That signal goes out through another connector, which is what wakes the automatic maneuver back in the main overview. On the right is the telemetry logging. It waits once for the phone to set the time, then every 60 seconds it records a snapshot. Power, charge, position, distance, and temperature. If the phone is connected, it sends a snapshot over. If not, it holds onto it in storage until the next connection.
Section of the software backbone, we see a drawn picture of how the Bluetooth link is actually transmitting and receiving data from the ESP32S3. Mode data, directional data for driving, and time data and weather data is sent from the mobile client to the ESP32. Data received out of the ESP32 is temperature data, battery percentage, state of charge, distance traveled, and power.
Here is a quick look of the phone app for Solaris. On the left side, you can see the landing page where you can log in or sign up. In the middle is our login screen, where a user can log in through Google, Facebook, or with a pre-registered email address. On the right side, at the top, you can see the different telemetry readouts, either the most current reading, or you can scroll and see bar graph of averages throughout the previous day, hour, week, etc. On the bottom, you have our mode switching, where on the very right side it is a manual mode, and you can see the joysticks where you can send throttle or steering commands. There are three buttons: manual, automatic, and stationary, where you can set the mode of Solaris.
On this slide are partial testings of our subsystems. One test involves ultrasonic testing, making sure that the distance readouts were accurate based on what voltage we supplied them. Other testing involved energy monitor unit testing, making sure that we were getting accurate readouts out of our energy monitor. Light sensor testing, making sure that our phototransistors were seeing proper light drop based on resistor values. And then lastly, motor plus encoder testing, making sure that we could control the motors properly based on encoder logic.
This slide sums up where we landed against our requirements, and the short version is everything we set out to do we hit. Starting with the performance targets in the top table, we needed the rover to drive forward at least 0.3 meters per second, and we measured 0.39 during testing, so we comfortably went past that mark. The solar panel needed 30 degrees of tilt to track the sun through the sky, and we got a full 30. It also needed 360 degrees of rotation so it can follow the sun in any direction, which we also achieved. Therefore, all three requirements were accomplished. The bottom table covers the three operating modes, and this ties directly back to the flowcharts we had talked through earlier. Manual control, where the panel drives the rover from the phone, works. Stationary mode, where it parks and tracks the sun in place, works. Finally, autonomous mode, where it decides on its own to reposition towards better light, also works. Therefore, all of our requirements were achieved.
We can see that the total money spent was around $2,000. The bulk of this cost coming from the expense of the chassis, being $623, as well as miscellaneous components, which attributes to board reworks and extra component sourcing. Two other big costs of the project was the DC drive motors at $227 and the pan and tilt motors at $109.
Our team fairly distributed the workload of Solaris to cater to each of our engineers' strengths and desires. My responsibilities were power integration lead, mechanical assembly lead, and project manager. Nathan was the troubleshoot lead, parts acquisition lead, and lead historian. Ryan led the software and embedded programming development. Garrett held the responsibility of hardware and software integration lead, chief editor, and risk mitigation lead.